So, hello everybody, and welcome to the second day of the Megapolis School for Young Scientists. We're now live on YouTube, and we're ready to begin. Today is my pleasure to present you our speaker. She is Dr. Zhengzheng Zhou from. Hello everybody, and welcome to the second day of the Megapolis. I'm sorry. Dr. Zhengzheng Zhou from Zhengzheng University in Shanghai. She will talk today about extreme storm analysis and machine learning applications for rainfall prediction in urban areas. So before I will give a word for Dr. Zhou, I was just want to mention that don't hesitate to ask any questions. We're here to interact with you, and don't worry if you think that the question is stupid. We will try to shed a light on all these concerns that you have. So, Dr. Zhou, you're welcome. The floor is yours.
Okay. Thank you for Anatoly, your introduction. So also welcome. Thank you for the invitation for this online meeting. So today I'm gonna share some of our works in China. So about the extreme storm analysis and machine learning applications for rainfall prediction in urban areas. My name is Zhengzheng Zhou. I'm from Department of Hydraulic Engineering, Zhengzheng University. Actually, I would like to say I'm not familiar with most of your background, so most of my talk today will be very general. And I think the purpose of this lecture not only to gain your knowledge on specific field, but also to gain or to motivate your energy, your thinking about your own study. I think this is the most important thing about lecture. So maybe we get started from let's get started from a brief introduction about our university. Our university is located in Shanghai, China. I think most of you may heard about Shanghai. It is a very attractive and international city, one of the largest cities in China. Most of the areas are urbanized, and we have densely populated people, and also a lot of international companies, international friends here. So, and our university is located in the urban core area in Shanghai. We have total students over 35,000, and including international students over 4,800. And we have total faculty staff over almost to reach 3,000 now, because these data are not that new. So we have more staff now, and we have 29 school colleges. So some colleges like College of Architecture and Urban Planning, College of Design and Innovation, College of Environmental Science and Engineering, and School of Ocean and Earth Science, and so on. These colleges and schools are very good and very famous in China. And also our university is among the top 10 universities in China. So if you have interested in coming to China or visiting China, you are also very welcome to come to our university. So our college is College of Civil Engineering. This year, our college ranked the #1 in the discipline of civil engineering in the world in the latest AWU and US News ranking. So our college, almost civil engineering is the top major in China, and also now is over among the world. We have many staff members and full professors and also associate professors, lecturers in our college. And we have 5 departments, including in structural engineering, geotechnical engineering, bridge engineering, disaster mitigation for structures, and also our Department of Hydraulic Engineering. Then something about myself. Now I work in Department of Hydraulic Engineering as an associate professor, and I received my PhD in my university in 2017. And I also have 2 years working experience as a research collaborator in Princeton University. My supervisor there was Jim Smith. He was a very nice guy. If you have interested in my research or our research, you're very welcome to search our publications. And my research interests mostly focus on urban hydrology, including extreme rainfall, extreme flood, hydrological modeling, and now we focus on climate change or urbanizations a lot. So today I'm gonna share with you 3 parts on extreme storms in China and extreme storm analysis and machine learning based rainfall prediction. So first is the extreme storm in China. Actually, the extreme hydrometeorological event in China, there are various types like heavy rainfall, typhoon, heat wave, drought, sand dust storms, and so on. And we have some features like high frequency, like heavy rainfall in city. We can hear the news every year, especially in the flood season. So there's also strong or pronounced seasonality, like the flood season or plum rain season, which is impacted by the monsoon. And it also has very high consequence, a great loss of life and the property. So these extreme events are very important, or we say of vital importance in China. So especially last year, maybe some of you have heard, it's very severe natural disaster. It starts from 17th to 23rd July. It caused deaths almost reached 400. And there's a great economic loss, over $20 billion, right? So that heavy rainfall, I mean the maximum hourly rainfall reaches 201.9 millimeters. And the maximum total rainfall during these days is 589 millimeters, which is very, very big. Because, you know, in that area, the annual mean rainfall is just about 668. So during that 6 days, the 6-day rainfall accumulation almost reached the annual mean rainfall. So this is a very severe disaster. So the extreme storms can cause urban flood. So here we got a definition from FEMA, the definition of urban flood. So it is defined as the inundation of a property in a built environment, particularly in more densely populated areas caused by rainfall on increased amounts of impervious surfaces and overwhelming the capacity of drainage system. So we can find 3 components for the urban flood, including extreme rainfall, less capability of drainage system, and increase in imperviousness. And in our study, we focus on the extreme rainfall. And also under the changing environment, especially caused by the climate change, the extreme rainfall becomes more complex, so which causes more our research to focus on this problem. So like, I think most of you have heard about the climate change and the global warming. So it is unprecedented in more than 2,000 years. So from the IPCC report, we can see that global warming causes more problems in the nearby future. So it is a very urgent problem. And also in China, we say China is a country with the fastest urbanization progress, especially during the past 20 or 30 years. The urbanization progress is very speed up. So caused by the climate change and urbanization, we are suffering more frequent extreme rainfall, especially in the megacities like in Shanghai. We see the area where extreme rainfall occurs frequently overlap with economically developed urban area. So this is a map of the annual precipitation rate of change in China from 1961 to 2020. So we can see that in this area, where Shanghai is here and Beijing is here. So we can see that in this area, especially in the Yangtze estuary, lower estuary, we can see that the rainfall change increased a lot, more than we expected before. So our motivation or our thinking, our question in our head is that, how did the extreme storms change in urban area, and how to estimate it for hydraulic design standard, and then how to predict it. So it is about the past, the current, and the future. So motivated by these problems, we talk about the spatial temporal variability of extreme storms in urban areas. These are our related publications. If you are interested, you can have a look at it. So about the spatial temporal variability of ES in urban areas, first we need to extract these events, and then we try to find the dominant generation, which is called storm types. And then we're gonna examine the spatial temporal structures from temporal variability, from the spatial variability. We examine the interannual or interannual change. And from the spatial aspect, we examine the location, the size, the coverage, its movement, many aspects. And the impacts, we're gonna examine if the climate change or human activities have a big impact on it. So here we just show two cases. One case is in 4 megacities in China. The another one is the Charlotte metropolitan area in the US. So here we just use 4 megacities, but in China we have now we have 11 megacities. Here we just pick 4 representative one, Beijing, Shanghai, Guangzhou, and Shenzhen. Guangzhou and Shenzhen, they are very close and very close to Hong Kong. So they are also located in different time zone because China speak, so they are located in time zone with different climatic features. So their rainfall characters are also different. Also, the 4 cities experienced a different degree of the urbanization, but mostly, especially in Shanghai, you can see the most areas are developed. But in Beijing, the north parts are still cropland or forest. Because in Guangzhou and Shenzhen, there are also coastal cities their shape and their size are smaller than Beijing and Shanghai. So they have different land use and different development strategies. So here, the rainfall data, where we can have data. One source is from China Meteorological Department. Another source is from the satellite. So here we use the data set from Global Precipitation Measurement Mission, which is downloaded from NASA. So the study period we used here is from 2000 and to 2020. The spatial resolution is 0.1 and the temporal resolution is 30 minutes. So one important thing we need to answer is that how to describe the spatial temporal ability of rainfall in a quantitative way. So before we just use a qualitative way to visually to describe the spatial clustering, but now we are thinking how to describe it in a quantitative way. So from temporal analysis, it's quite straightforward and commonly used MK trend test, L-Petit test, or sense slope method, which can examine the trend or the change point. In spatial analysis, which we're more interested in, is we use some geographical analysis method like global Mollens I and local indicators of spatial association and the semi-variance. So so they can use to identify the level of the spatial clustering and also to identify the location of its clustering and also identify the range of the clusters in different directions. So first about the temporal variability, here we use annual maximum 3-hour rainfall as a representative to describe the extreme events. So first we can see the magnitude of the ES, the increase from north to south. So like in Beijing, the rainfall, ES rainfall is relatively lower because it is in the north. But at Guangzhou and Shenzhen, the ES storm magnitude are much greater. And one interested in seeing that using MK analysis, we found that from 2000 to 2020, the ES didn't have a significant increasing trend in the 4 cities. So maybe it is caused by the relatively limited length of the data record. Also, maybe about the most development is urban development is happened before 2020. So in this period or developed area, they do not have significant temporal trend. But interesting thing that we're going to talk about later. Interesting that we found that they have a strong cluster features in the space. So here we use Mollens I and the CV to identify the spatial heterogeneity or spatial variability. Like in Beijing, we can find that the Mollens I is not that high, but they have a moderate, like Beijing's here. They have a very relatively high Mollens I and are about not moderate CV. So we can say that in Beijing, yes, is highly clustered in space, but there is a relatively little difference in rainfall magnitude between the clustered areas and the rest part of the area. And the other characters we can find in Shenzhen, Guangzhou, and Shanghai. We can find the 4 megacities. They have different features, different patterns of spatial clustering. But like Shenzhen and Guangzhou, actually, I'm not that satisfied with these results, because the shape is a factor that impacted our research result a lot. So this is what I mean. Just now. So we from the qualitative analysis to quantitative analysis. So we use a Lisa map. We can find the location of the spatial clustering. Right. It is quite obvious that in Shanghai and in Guangzhou, the clustering is very pronounced. And we also use the semi-variance. We first use the semi-variance to examine the change of the rainfall, but we didn't consider the change of the rainfall in different directions. So mostly we can find that they can reach a stable value within the range of lag distance, which demonstrate that each range of the ES clusters are smaller than the city scale. And like in Shanghai, we can see that in Shanghai, the distance where the variogram reaches the seal is here, is around 4.84. So indicating that the ES extends to a scale of 48 kilometer. And then we examine the spatial cluster in two directions, from north to south and from east to west. So we can see that in different cities, we find different clusters in two directions. Like in Shanghai, we can see that there is a balanced pattern between the transverse and the longitude directions, right here. But in Beijing and in Guangzhou, in Beijing and Shenzhen, we can find a transverse east-west clustering pattern. In the Guangzhou, here Guangzhou shows longitude north, means north to south clustering pattern. So we can see the big difference. So we can see the big clustering in Guangzhou and moderate clustering in Beijing and Shanghai, but lower clustering for Shenzhen, which is, I think, is impacted by the shape and the size of the city. And then we also examined the influence of the urban growth on spatial heterogeneity of rainfall. So through MK test, Molan's eye in Shanghai shows a significant increasing trend. So we question that if it is related to the urbanization. So we use Shanghai as an example to examine if the urban growth impacted the spatial heterogeneity of rainfall, and we find that this is land use, 3 land use map in 21 and 2015 and 2017. We can find that it is almost quite paired with the spatial distribution of the rainfall. But the range of the rainfall clustering did not change that much. So we have a short summary is that a quantitative framework is constructed we can use to evaluate spatial heterogeneity in space quite well. And the short duration ES is highly clustered in space from north to south. We find it's clustered, but with different features and in different directions and in different range, right? And we also, it is very likely that the urban growth plays an important role in the change of its spatial clustering. So case study 2, we use Charlotte metropolitan region in US as example. So this is a paper we published on the HAS. So the title is the role of storm scale, position, and movement in controlling urban flood response. So in this paper, we examine if the spatial heterogeneity of rainfall will impact the flood response, like the flood peak or response time, like these. So we examine the following questions, like how does rainfall scale interact with basin scales in determining urban flood response? If the position of a storm influence the flood response, in how the storm direction and its movement impact the flood response. So these are very interesting questions we have explored in this paper. So we use some index to indicate the rainfall, like total rainfall depth, maximum 15-minute rainfall intensity, and like the flood index, we use the maximum normalized flood peak and total runoff volume. And one interesting index we used is which consider both rainfall and flood, is that we use a rainfall weighted flow distance. So we use a flow path for each grid, because our data is gridded. So we use for each grid we can compute the flow distance, and we use the rainfall as its weight. Then we can have we can have a rainfall weighted flow distance to describe the rainfall location relative to the flow path. So here we just use a box plot to show the different distribution of rainfall and runoff. A general conclusion from these figures is that we can find that rainfall and runoff, they have different features. So what impacts the this match between rainfall and the flood? Rainfall and flood, we think maybe it's rainfall itself, the rainfall spatial structure, and also the land use, the urbanization. So here is a question we consider that flood peak is related with which impacts. So from this scatter plot shows the rainfall coverage, the relationship between rainfall coverage and the flood peak. So there's a tendency that we can see is that the flood peak increase with the rainfall coverage. So the top peak flow are generally associated with 100% basin coverage by the storm core, which means that, and I think it's quite easy to understand that for the very extreme flood, which is caused by the rain event, which is covered all over the basin, right? But one thing we find is that for some urbanized area, that some of the highest flood peaks, the fractional, the rainfall coverage is below 100. So maybe it is caused, so maybe it is associated with the urbanization effects, because it has drainage system, and the drainage system is over capacity and it carries more runoff in a very limited time. So maybe the urbanization changed the upper tail of the flood peak distribution. And this scatter plot shows the this lag time means response time. So the response time means from the rainfall peak to the flood peak. So this for this period. So we can find the features between rainfall and flood, right? So Actually, we found less correlation between response time and the rainfall location, and we found less correlation between flood peak and the rainfall location. But we do find some interesting findings in the flood peak and the movement of the rainfall, right? So here from this figure, we can see that the very large flood peaks tend to occur for gradient. This means the speed. So this means the speed of the rainfall movement, right? If the speed is close to 0, means the storm is almost stable, right? So we found that for that very extreme flood, the rainfall almost stable, right? Or the zero rainfall movement tend to associate with longer lag time, while fast moving storms tend to be associated with very short lag times. So the second thing the second motivation of our study is how to estimate extreme storms for hydraulic design standard, which we're gonna use for our current engineers, right? So this is very important issue is that rainfall frequency analysis. So we use the stochastic storm transposition to do the rainfall frequency analysis. So first, maybe you are not familiar with this part. If the rainfall frequency analysis or the flood frequency analysis, they're closely linked. They are used for designs of hydrological structures, like maybe you have heard return period or the frequency. So you know, for this part, the rainfall frequency analysis, we provide intensity, duration, frequency curve for the design of some water or hydrological infrastructures. But the problem in the conventional approaches, like the alternating block method or almond method, like most of the conventional approaches, they use the data from the rain gauge, and maybe they will miss the real maximum rainfall rate, right? Because we know that the rainfall distribution over the entire basin is not homogeneous. So if you just use the rain gauge at this location, you may lose the real location of the maximum rainfall rate, right? So it will not safe for the design of the watering structure. And also we have a very ideal assumption that basin averaged, or we use uniform rainfall over the entire basin. And we also use assumptions of temporal structure, like the rainfall time series, it's just like these, right? But actually the rainfall could be like these, or then more than one peak, like 2 peaks, right? So these assumptions will increase the uncertainty of the design results, right? So here we developed a new method, which is called stochastic storm transposition. In short, we call it SST, but not the sea surface temperature. It is stochastic storm transposition, right? So I just show you a very basic idea about this method. Like we will first identify a domain where contains our target area, and also area with similar climatic features area, right? Then from this entire area, we will extract extreme storms, right? ES storms, and make them into a storm catalog. So a storm catalog is very important, which contains a top like 100 or 200 storms in the entire area. And then we use a transpose method to, for example, the real storms happen here, and maybe we can transpose it here, right? So we can, so then we can compute the rainfall experience in this area, right? So then we can recreate T years, like 100 year or 1000 years annual rainfall maximum, and then we can generate the estimates. So the advantage of this method is that we can use the regional information, not only the information in our target area. We use information from a homogeneous or climatic area with similar features as the target area, right? For example, this is a storm we extracted before, and we can see that the maximum rainfall is not happened in this area, but we can transpose this storm to our target area, and then we can have a more informative information for our estimates. So this example we have generated in Dead Run area in the US. So in this area, has very complex terrain, like the mountainous area in the north, in the Chesapeake Bay area in the east. So make this area the climatic feature, the hydrometeorological feature, it's very complex. And just to mention, we talk about the storm catalog. So we examine the spatial heterogeneity of rainfall, just we have done in the 4 megacities in China. We use the rainfall map to diagnose the spatial heterogeneity. Like the black dot indicates the location of each storm event. So actually we have 200 storms in the storm catalog. So enough storms, we can examine the information, the key information in these events, and then we can use this information to generate our rainfall estimates, right? So this is a more informative and a more useful, valuable approach, right? So from this map, we can see there is a trend, southwest to northeast trend, the spatial gradient in heavy rainfall activity across this domain, right? And also corresponding to an increased spatial trend from inland to coastal area. So it is quite common knowledge that in coastal areas we suffer more extreme events, right? And the maximum in the occurrence frequency and mean rainfall in the eastern portion of the study between Baltimore area, here is Baltimore City, and the Chesapeake Bay, right? So these two maps, the red map shows the probability density of the storm occurrence over this domain. So the black dots in these two pictures are same. Okay, so the blue just shows the rainfall magnitude, and the red shows the probability. Okay, so this is closely linked to the complex topography in this area we just mentioned, right? There is a mountainous area, and it's a falling zone. It means the elevation changed a lot significantly from this area in a coastal area, which impacted these climatic features. And we use 50 most extreme storms in the catalog to examine the extremes in the extremes. their characters, right? And we also examine the storm types. So the red one means the storms caused by tropical cyclones, and others means the black means the thunderstorms, and the gray means the other storms. Okay, so we can see that most storms are caused by the thunderstorms, right? So we also, for the storm catalog analysis, we also examine the properties of the storm occurrences. We compare the interannual and interannual distribution to see if there's any trend in the storm counts, or there is any pronounced seasonality in the annual distribution. And from these figures, we can see that there is a pronounced seasonality almost in June and July, right? This is similar feature in China, and there's only one peak. So there's only one like the more frequent period for the extreme storms. And for storm types, we just mentioned, so this area is dominated by the warm season thunderstorm, as the last figure shows. So we generate the IDF curve. We just mentioned intensity, duration, frequency curve. We compare the result with the conventional method, which is carried out by NOAA Atlas 14. And from these figures, we can see that our result is is close to the results from NOAA, but the most advantage of our method is that we can provide more complex, more real spatial temporal structure of the design storm, which is very important because we have just mentioned that the spatial temporal structure of the rainfall will impact flood. So flood will impact people. So we can say that spatial structure of rainfall is quite important. And from our results, we can see that the ideal design assumption is that the one peak or the peak in the middle is not that accurate for everywhere. Like in this area, we can see maybe they have two peaks, or they have more peaky area, or they have different time of the peak, not just in the middle, right? So this gives us more hint to motivate more research for the future. And how to use our results into the urban flood. So here we talk about the application of the SST in hydrological modeling. So coupled with a hydrological model, we can examine the relationship between spatial temporal variability in rainfall and flood responses. So here we use a geisha, a physical-based model to examine it. And we generate rainfall scenarios with different return period, and just drive the model. And we can see that here is a violin plot which shows the flood distribution and the rainfall distribution. And similarly, as we talked before, we can see a mismatch between flood and rainfall. So which is definitely caused by the spatial structure of rainfall, even for this small area. You know, this area, the study area is only 14 kilometers, square kilometers. So it's really a very small urban area, but we still find a mismatch between flood and between rainfall. So this gives us very big enlightening about the next work. But there's but for the response time, we just talk about the peak to peak time, right? Rainfall peak to flood peak time. But they show similar features under the different return periods. So for the small return periods, this is for small return periods. This is for large return periods. So for large return periods means the extreme storms are greater than the small return periods. In the time series of simulated hydrograph based on our 3-hour design storm, we can see that the rainfall, the flood hydrograph is also complex. So we can conclude that the flood peak is quite associated with the rainfall structure, and even for a small, densely urbanized urban area. And we can also see the different flood distribution among the sub-basins in this area, like from DR1 to DR2, 3, 4, 5, and the basin outlet. They show the different flood distributions. So we say that the flood distribution over the entire region are different, right? And here we can also examine the features of the spatial temporal structural rainfall on the flood peak. So under different return periods, the impact, the role, also we say the role of the flood structures, rainfall structures are different. Like for the 10-year return periods, here dispersion of the rainfall weighted flow distance is more important, right? But under the 200 years, the impact is lower, but the peak rainfall rate is more important. So we can find the different rule of the spatial temporal structural rainfall that impact the flood peaks. And there's also conventional, or we say commonly understanding that the relationship between design storm and design flood, they are same. But our result shows the return period of rainfall and return period of flood, they are not equal. They are not equal. So that means the commonly assumption between design storm and design flood cannot be held. So how to compute the real relationship between them? This is still unsolved problem. So in our newly published paper, we also discussed about the different role of spatial structural rainfall on rainfall frequency. So this is a very interesting paper that we coupling SST with copular function, and we can examine more. We can understand more about the ES event. So summary, I think the summary is not that important. So let's just go to the next. So how to predict it? It is about the future. So here I'm gonna talk about the machine learning modeling for the predicting long-term monthly rainfall with an ensemble climatic and meteorological predictors. Actually, so at this stage, we just predict long-term rainfall. We do not predict, we still do not predict the extreme storm. This is our future plan to do that. So here I just give you a very brief introduction about how we do that before. So actually, artificial intelligence is not a new concept. It has been used like for over 50 or 60 years. So, but at that time, when it was first proposed, at the time it was limited by the computational efficiency and people's understanding. So it's not widely used. But now you can see machine learning, you can see AI everywhere in our daily life, right? So even everyone have the smartphone, you cannot avoid it, right? So then then we have the idea of machine learning, and then we have deep learning. So this figure shows the relationship between three concepts, right? Most people, they're confused about what their relations, right? So there's one thing I want to mention, that we do not develop the machine learning algorithm or deep learning algorithm. We just want to extend their usage in our hydrological field. So we want to use a state-of-art models to solve our problem in our field, right? So in this study, we used 25 stations in the lower reaches of the Yangtze River. Here is the 25 stations. And we use a monthly rainfall from 1950s to 2015s. Then we use an ensemble of predictors, which help to provide more accurate result. We have local predictors, we have large-scale climatic predictors, local predictors like monthly temperature, pressure, wind speed, water pressure, humidity, wet days, sunshine, like that. And large-scale climatic predictors, we have ANSO index, and we also have the monsoon index, because I have mentioned that this area is significantly impacted by monsoon. So the flow chart of our study is quite straightforward. We have the original data, and then we do normalization, and then we divide the data into two parts, right? Training test and the testing test. Training test, we have the N types of predictors and the rainfall, and we use a model to train the model and build the prediction model. And then we use a model to test if it can predict the rainfall in the testing set. And then we compare the real rainfall and our predicted rainfall. We use some evaluation metrics like RMSE, MAE, and then we pick the best models for each gauge. And here's a model we use, like ANN, RF, GBR, SVR, and DRNN. So as I mentioned, we do not develop models, so we just do hyperparameters in these models. Then we can train our model. So our basic results is that first we compare the model without predictors and the model with an ensemble predictors. And from these figures, we can see that the model with the ensemble predictors produce lower error than the plain base model. So we say the ensemble predictors help to improve the accuracy. And another thing we have found that actually for different evaluation metrics, we have different performance of these models. So actually we found that model performance varies over the 25 gauge stations. And just relatively random forest is better than others. And we also examine the importance of each predictors, and we found that the local variables like humidity and sunshine duration are the most important predictors, improving our accuracy. And like for the large climatic predictors, the 4-month lagged monsoon index is higher importance than other large-scale variables. And we also found that the accuracy of the model prediction is different. Like in summer, where the rainfall magnitude is higher, the accuracy is relatively lower than that in winter. I think this is very interesting phenomena. So from the first stage, we find that there's no simple model which can be used for all the stations, and different model has different structures and different advantages. So we have questioned that how to use all the advantages of each model. Then we think of another way. So we use a stacking ensemble learning model for the rainfall prediction. So here we just use several stations as an example. So the main flow chart of the prediction procedure are quite similar, but one thing is different is that for different models, we try to have their weight. For different models have the weight, and then we combine them together. Then, so this means we combine the advantages of all the models together, and then we produce the our final results. So this kind of model, we call it a stacking model, right? So so the general results is that there's still no one model can apply to all the stations, right? But generally the stacking models can provide better or more robust result than the single base model. So the stacking also can strategy reduce MAE more effectively than other evaluation metrics. So and also we find different performance in different seasons, and also in different dry periods and also wet periods. They have different accuracy. So this is a problem that we want to solve now, because the model we used now is very we say black box one, but if we can put some physical law to train the model, maybe we can have better results. So these are the publications we have published these years. If you're interested in these topics, you're very welcome to have a look at them, and you're very welcome to discuss. And a very short summary that extreme storms is a very important issue that needs further explore under the changing climate, which is caused by the climate change, caused by the urbanization, human activities, right? This is a hot issue. And still, we lack the understanding of this problem. And we also encourage young scientists like you guys to join us to solve the ES problem and solve the ES related problem, right? Like the flooding problem and also typhoon and also tropical cyclone problems. But maybe like typhoon or tropical cyclone is not common happen in Russia, but still it is a very interesting and very important problem. And very lastly, very welcome to our university and very welcome to work with us. So this is my email address. If you're interested in our group research, you can come to ResearchGate or School Scholar, even my personal website. You can have a look at them, and we can communicate more, because for the lecture, I can just provide you some very general information. For the details, we still need like further discussion. Okay, thank you for listening. So you have any
Joyce,
questions?
thank you very much. It was really impressive. So before any questions arise from you guys, I just wanted to ask you, Joyce, to share with us papers you mentioned, if it's possible to make some archive or zip file or maybe Google Drive folder with papers you used in this tremendous presentation, it would be really perfect, because
Oh, okay.
for myself, I would be really interested to go deep down in your research and to take a look closer. Okay, so if anybody has any questions, please.
Can I ask a question?
Yep, sure.
My name is Artem. I'm getting a master's degree in Moscow State University in Land Hydrology department. First of all, I would like to thank you for your presentation. It was really interesting. And also, I would like to say that I'm working in the same field. I'm trying to make a model based on neural networks that can predict river flow in European part of Russia. So that's why I got some questions about your machine learning part of the presentation. And the first one, you mentioned that you used several algorithms, used random forest, gradient boosting, some other based state-of-art algorithms. And the last one was some kind of recurrent neural network. Am I right?
Yeah.
Yeah.
Can you? Yeah. DARN.
Yeah. Can you say something more about that algorithm? Because I'm using recurrent neural work too. I'm using LSTM. Maybe you know such kind of. Yeah, and I never heard about this one, and I would like to know more about that.
Okay. Did you ever heard RNN without DA?
Of course, yeah.
So it just put attention and before attention module before you use the data, and then recurrent it before you produce the result. I think if you search it on Google, you can find it. But it's not that commonly used actually. And about LSTM, actually we tried this before, but for our stages we do not find it quite work well, so we just quit it.
Okay. Okay, thank you. So I got some more questions. You mentioned the predictors. You used temperature, precipitation, discharge, and you also mentioned that you used El Nino. Am I right?
Yes, we use that. Yeah.
So what's the future importance of that feature of El Nino?
So
because
go ahead.
Yeah, because there was a slide with a future importance graph, and there wasn't information about El Nino. What's the situation with that predictor?
Actually, as I mentioned, the research, the study area, it is a coastal area, so it is quite impacted by the monsoon. So for the past studies, we have found that the rainfall is quite associated with ENSO and also monsoon. But it is still unsolving problem, because like we not use like the ENSO index in July, and we also use the ENSO index the last year, like 4 months or 3 months. We tried that. So actually our results find that so there's a lagged relationship between ENSO and the precipitation, like the last year the monsoon the ENSO index last year impact the rainfall this year, like this is our findings, right? So I think similar findings have been found in Australia and also in India. I think this is a common phenomena.
Yeah, I heard about that, but yeah.
For the practical part, you need to try. Just try many, right? You know what I mean? You just put
I know,
the
what you
figures,
mean.
right? Yeah.
Uh, yeah, but and so it's not really in my field of study because I don't think that El Nino affect on Russian rivers, but who knows?
Yeah, I know.
Uh,
Yeah.
uh, also, you mentioned the results of different algorithms, and am I right that you mentioned that random forest gave the best results?
Mhm.
So,
Uh-huh.
the most basic algorithm gives the best results, better than CNN, RNN. Am I right?
I mean, just relatively better. And as I mentioned that for different evaluation metrics, you had different results. You have different, like the ranking of the models, right? So like for MAE, maybe our RF is better, but for MAE, RF is like second place. But you know, we have 25 stations. We don't find like RF is best for all the stations. We just like for the majority, like 20 or 15 stations, we think RF is better. So I just say it's relatively better, but not that significantly or like very overperform others. Not that.
Okay, thank you. So I think the last question, I don't want to bother you with my questions. So you took 25 station, yeah? And
Yeah.
you predicted the rainfall on that station. So
Yeah.
the rainfall for the points. And it's not really a question. It's, for example, I get a problem now in my work. I also use mean precipitation, temperature, water discharge in points. And I also wanted to use, so all these parameters are time series, yeah? But I'm trying to apply some static parameters like elevation for
Oh,
water
I know.
shields.
Yeah.
But maybe you know something about merging time series and static parameters, because I can't solve that problem. I can't train my model train my model on time series and on static variables.
I know what you mean. If I understand correctly, you mean that you have some predictors you want to use, but they are not time series, right?
Yes.
Yes. So for my understanding, your predictors have already shared the information. They have contained the information of these non-time series variables. I mean, for elevations, for some others, so you mean I mean that like temperature or the flow, something they have already contained the information of elevation because they are impacted by the elevation, right? So even for the predictors, so different predictors, they also have some, they shared some same information, potential information, just you cannot or we don't try to formulate them, right? So I actually I don't know how to cooperate with them, but I have stuck with that problem too. But then I answer myself because you know, like for rainfall or temperature, actually they're closely linked with elevation or the location or other features. So you don't need to like stuck with that. But one thing I think is worth thinking that the spatial, because we just use a time series, right? But actually for different predictors, they have spatial correlations, right? So how to do the spatial temporal models for the prediction? I think this is worth thinking. Yeah, it is also our next work, because you know for rainfall they also have the spatial correlations for 25 stations, we can share informations together, and we can do the prediction together. So I think we need a model like that, right?
Yeah, I see what you mean. Okay, yeah. I understand now what you mean. So the time series predictors already have the information about the static predictors. Okay.
Yes.
Okay. I never thought about that. So
data, just the data, but if you put them together, there are many informations. So for
I know.
Even for some predictors, they share many same informations together. So even you can find that without one or two predictors, you can produce similar results, right? So this happens a lot. So you just use the key predictors you need, it is data factory, but maybe not produce the best productions. This is my understanding.
I see. So I will think about it. Thank you. I think it's all my questions. It's not all my questions, but can I write you mail or something about? I screen your slide. I got maybe some more questions about ensembling, but for today, I will stop bothering you. So thank you very much for your answers. It was very interesting lecture.
No,
thank you, Artyom. By the way, all contact informations about lectures are available on our website, so you are free to go there and send an email from the website.
Okay, thank you.
Does anybody have any more questions?
Yes, please. If I can ask some question.
Yes, please.
Thank you for presentation, and I have a little comment for Artyom. I thought I don't know a lot about neural networks, but I thought that if we have a static parameter, we can add one odd neuron to the layer and make it constant. But maybe I'm not right. So the question to our lecture today is about accuracy. You said that the accuracy was lower in summer. Yes, am I right?
Yes.
But the summer is a monsoon period, so the variability is higher.
Yeah.
Why do you think that it's strange that accuracy is lower?
You mean the difference between
higher.
Higher in summer? What is the reason? What is the reason to it?
So by accuracy is lower because the variability of rainfall events is higher, and the itself, and it's not strange. I mean, or there is another reason. Why do you think it's strange? It's not natural.
Actually, we expect that the accuracy is better in summer, because we want to explore the extreme storms, and extreme storms happen a lot in summer, in flood season. In China, we have flood season in summer, right? So we expect that we have better results in summer, but actually we find the opposite results. And I think it is linked to the rainfall variability, because in summer the rainfall magnitude switches a lot, and we cannot and the magnitude is much higher in winter. And then, in winter we do not, the time series is quite stable, but in summer it jump up and down, so it's a little bit hard to catch it. So this is what I say before, because we just use black box model, and we cannot like exactly believe it, and we better use some physical law to train the model. Even like if we, I don't know if you do the model before, because it's very tricky that even we have predict some rainfall below zero. This is impossible in our field, but for the model itself, it doesn't matter. It just produces. So
you had a lot of high events, lot of this high rainfall events, but accuracy was lower.
So I think we don't give the model enough constraints, right? So I think this is a very hard problem. But you know, we don't develop models, so you know, this is a hard way to go. So how to divide the model into several parts, and for which part we have some constraints for it. It can produce at least some results as a baseline. I think this is still a hard problem.
And the second little question about urbanized and non-urbanized areas is, as far as I understand, you compare the rainfall events in your first part presentation in urbanized areas and non-urbanized areas. And can you compare some? Is there some difference between mountainous urbanized areas and non-mountainous urbanized areas, and between non-mountainous non-urbanized areas? So can we compare these four types of territories in the sense of variability and other characteristics of high rain events? Can you comment this?
Thank you for your question. Unfortunately, we do not do the mountainous urbanized area before, you know, because the four megacities are all in the plum area. They are not mountainous. But for my understanding, that we don't want to compare them directly. We just want to know the features of them and solve the local, regional or local problem. But I think the mountainous urbanized area, definitely the extreme storms are different. Like in mountainous area, we have flash flood, right? Flash flooding, right? This is so fast. This is so extreme, which is different from the plum area. This is what I know, right? So
urbanized areas impacts more on the flood, and mountainity is impacts more to the rain. So the rain is much higher in the mountainous areas, and the flood is much higher in urbanized areas. Am I right?
I think the floods in two areas, they're different. Like in urban area, the flood, we sometimes call them just inundation, right? But for mountainous area, the flood is from the mountain is so flash. We call it flash flood, and even the river flood, or even the floods caused by the snow. I think they're different. In our research, we just show the trend that the urbanization changed the spatial distribution of the rainfall, but we do not find that for our study period, we do not find that the magnitude has changed a lot. So for our understanding, we think that the climate change is the main reason for the increase of the extreme storm, the magnitude, but the urbanization changed the spatial distribution partly. So for the more physical mechanism or explanation of this problem, I think we need more. We need the climate model, like Wolf model, to solve the problem.
Thank you very much.
I hope I
The method is
answered
very
your
interesting,
question.
and probably I'll write you after. Thank
Okay,
you.
sure.
Thank you, Nikolai. So anyone else? By the way, Joyce, I have one question. Honestly, it is about the beginning part of your presentation. I'm curious about the change point analysis you made. So I'm curious, why did you choose petite method for this transition analysis? Because as far as I know, this method is only for single point detection. And what if we have more than one point, one breakpoint?
You mean the trend analysis?
No. I think it was before. You wrote about petite method.
Yeah.
Yeah. So next slide.
Here, the petite test.
Yeah.
Oh, yeah. So this is a change point. We you mean the rainfall we use is basin rainfall, and how to do that for just a single point?
No. I mean, this method, this test, is designed for detection of only one breakpoint. So it is a single breakpoint analysis. And what did you do when there were more than one breakpoint in the time series?
Oh, good question. But unfortunately, we don't find the change point in our time series.
Okay.
So yeah.
Okay. Luckily.
Yeah, luckily.
Okay.
Yeah,
Okay,
but I'm sorry. Actually, I don't remember the tests exactly because mostly from our experience, we do not find that many change point. But I remember once we can find 2 or 3 change points use this test, but I cannot remember exactly how we conducted it. We just watch the slope and we can find the different the shape of it.
Okay. Thank you. So let me check the YouTube. Okay. So it seems that we have got no more questions, and the time is almost up. So then, on behalf of our organizers, I would like to thank you very much, dear Joyce, for this tremendous lecture. I think we have really nice discussion afterwards. So thank you very much again, and I'm looking forward to work with you in the future and to stay in touch. Thank you.
Thank you, guys. Thank you. Nice talk. Thank you.
Yeah. So thank you very much, our participants, for attending the lecture. Looking forward to see you tomorrow at 4:30. We will have a lecture by Michael Marker. So today, that's all for today. Thank you very much. Bye.
Bye.